Good afternoon, everybody. This is lecture 20. Actually, forgot to change this first slide. So, this is lecture number 20. We are continuing with backtracking, and what we did last time is to study how we represent our problem in the form of state space trees, which is just it's not an actual tree, the tree data structure that we have studied earlier, but it is just a representation of all the possibilities that can arise in case while you are finding a solution to a particular problem. So we did fixed tuple state space trees and variable tuple state space trees, and we solved the sum of subsets problem with that using both the types of trees. And then we also talked about static and dynamic bounds. So there was also the concept of implicit, in the sense uh, when you make a state space tree, it is implicit in the sense that uh, it's not actually there, but it is understood that we are trying to explore the solution considering this state space tree in the picture. So we are actually building the tree, and we explore a node only when there is a uh, possibility of finding a solution. Otherwise, your state space tree does not actually exist there. You start exploring, and you explore only when a node is feasible. So the problem that we are going to do today, again backtracking with bounds, is for 0 1 knapsack. So actually there is another concept of branch and bound, which we apply along with backtracking, of course. So since the state space tree is not actually physically present anywhere, it is just implicit, it is understood these are all the possibilities of a solution that we can have. We will branch to go to a particular branch of the tree only when it is feasible, and if it's not feasible, we say that we have bound it there. For example, we discussed the static bound in case of sum of subsets problem. The static bound is that if you get to a node with a sum more than the sum you're looking for, then that becomes the static bound, and dynamic will vary. We'll see another example of dynamic bound in today's problem. So this is what we were discussing last time. So now we are going to do backtracking for 0 1 knapsack. 0 1 knapsack is an optimization problem. So we are dealing with, are not only supposed to find a solution, we have to find the optimal solution. So for optimization problems, what we do is we define 2 3 things. One is, because it's an optimization problem, while you are exploring the tree, the state space tree for that particular problem, you might encounter different values. For example, in knapsack, if I pick up only one item, that also gives me a value. But what I have to check is whether my value is the best value, or if I am exploring my tree, what I'm getting now, is it better than what I got before, or is it worse? Okay, so that is one thing you have to keep in mind. It'll be more clear once we do the example. Then value is something, the value that we are looking for. What is the profit, or what is the maximum value we can get out of a 0 1 knapsack? And then you have the concept of a promising node. So a node is promising only when it is giving you more than what you already have. If you already have that, the node is not promising, and you need to know how to check whether a node is promising or not in case of 0 1 knapsack. In case of sum of subsets problem, if you are at a node and the sum is less than the sum you're looking for, so it is a promising node, because adding more elements can give you the actual sum you're looking for. So what is promising in case of 0 1 knapsack? Ideally, promising node is one that can give you a better value or more value. So how do we calculate that? What a node can give us? We have to see that. We'll see that in the solution. So what is the best solution that you have? So best is, initially you initialize it to something which is, you can say, the worst possible solution. So what is the worst possible you can have in knapsack when you can are not able to pick up any item? So my value is 0. 0 is the worst I can get when I'm not able to pick up any item in my knapsack. And then we keep on modifying it as we move ahead. So what is better? A better solution in case of maximization problem would mean a value larger than your current value, and in case of minimization it will be value smaller than your current value. So now what is promising? A node is promising when it is feasible. Feasible is, for example, when you are solving a knapsack problem, you will get more profit, but if you are exceeding the weight of the knapsack by picking up that item, it is not a feasible solution. So that's why when we do it using dynamic programming, we use minus infinity. That means it is not a feasible solution because there is a weight restriction. So a feasible solution, the promising node should be feasible, and it is promising only when you can get better than the best you have at that point. Otherwise it is a non-promising node. What is the bound? For example, in case of knapsack, a simple bounding example would be, if any node gives you a negative weight, for example, you pick up that item, put it in the knapsack, you have to take out that weight from the weight of the knapsack. So getting a negative weight is obviously not a solution. So if any node gives you a negative weight, then you can just bound or strike, prune that tree at that point. Then that is one bound, that is static bound for your problem. And what will be the dynamic bound for this uh, 0 1 knapsack or optimization problem? So if you have to check uh, the what this node promises you. If this node is promising you something better than the best you have right now, then it is a promising node, you go ahead. Otherwise, if it promises you something which is less than you already have, so you can just strike off that node for and explore something which is better. So okay, we just get to this. You can have an upper bound or a lower bound depending whether your problem is maximization or minimization. So uh, before I go here, let me just go to this problem. Okay, this is a 0 1 knapsack problem. Okay, so item 1 to 4, uh, pi is the value, vi actually the value of the item. This is the weight of the item. This is the value per unit weight, vi by wi, that we used to calculate. If you see, it's already arranged in descending order from the highest weight value per unit weight to the lowest unit weight. Now, this is a 0 1 knapsack. This is not a fractional knapsack. But if you look at it, fractional knapsack, whenever you have a problem and you're asked to solve it with 0 1 knapsack, so you will always have, you might have a situation where your knapsack is not completely filled because of the weight issues. But in case of fractional knapsack, even if you have 1 unit of weight left, you can fill it up using a by fractionally by some item. Okay, so obviously fractional knapsack will either give you something, either give you the solution that 0 1 gives you, or it might give you a better solution. So if you think of it, what is the best solution you can get for a knapsack problem without mentioning whether it's 0 1 or it's fractional? Fractional will always give you better because it will always help you fill in whatever units of weight are left in the sack. So what we do is, considering our fractional knapsack is will give us the best solution. We will find what is the maximum profit we can get out of this problem. And how do we calculate this maximum profit? We'll calculate it using fractional, because 0 1 will not give you more than that. At the most, it will give you the profit that fractional gives you. It depends on the weights of the items and the weight in the knapsack. But it will not give you more than that. It will obviously give you equal to or less than that. So first we calculate what is the maximum possible profit. So how do you calculate fractional knapsack? You have you pick up this item based on the values per unit weight. Then you pick up this item, so you have used weight 7 till now, and the profit is 26. Then out of this 10, you cannot pick all the 10, so you'll pick up only 9 units, and that will be 45. So the total will be 71. So 71 is the maximum profit you can get. If you just look at this problem in the 0 1 knapsack way, just look at it. You can either get this. There are three options: 10 and this 10 and 5, 10 and 5. Then if you pick up 10 and 5, you get a value of 80. If you pick up this 10 and 5, you get a value of 60. If you pick up 5, 5 and 2, you get 80. Sorry. Oh, we did this. Okay, this is nobody pointed out, so everybody is sleeping. So okay, let's do this one. We'll get to the fractional knapsack again. So what is the other option? You have the other option is 10 and 2, and if you do that, you get 90. So the maximum you can get is 90. Fractional, when we are picking first two items, we get 70 plus 45. So we are actually getting 115. So 115 is the maximum profit. And here you see in fractional, you get either 60, 80, 80 and 90. So obviously 90 is the highest fractional knapsack will give you. Okay. So 115 is the maximum profit for fractional knapsack for this same problem. This problem is 0 1 knapsack. So fractional tells us that this is the maximum value that you can achieve. So what we will try to do in our optimization problem, we'll try to aim closer to 115. So we obviously will not get 115 because we have the restriction of weight as 16. We might exceed that weight to get we might not be able to fill it completely because of 0 1 restriction. So but we'll try to grow as closer to 115. Now just erase this. Now our max profit is 115. Okay, when can you have a profit of 115? That is when you have all the we can have a profit of 115 when you have all the 4 items available. Okay, so if at any point you are making a decision whether to pick or to leave one, you will have only 3 more items left. So if you have picked one, you can still expect to get to 115. But if you have dropped one, that means one is not no more in your consideration. So what is the maximum profit you can get? So the maximum profit that we are looking for is again by using fractional knapsack. So apply fractional knapsack on these 3 items only. And what do you get there? So fractional knapsack, you pick up items in the order 10, 5 and 1 unit from this. So that is 80 plus 1 unit is 2. So 82. So if I have only 3 more items left in consideration, 82 is my maximum profit. So the maximum profit that you calculate at every step will also change based on your decision whether you are picking or leaving an item. If you are picking item 1, you still have 115. If you are dropping item 1, your max profit goes to 82. So the 82 is the maximum you can achieve if you are dropping item 1. Similarly, when you reach to the next stage, so what I'm talking about is this. So you were here, I'm doing the fixed tuple state space tree, for example. So I pick up or I drop item 1. So my max profit would still be 115. If I'm dropping, it drops to 82. Then again, here I have to make a decision. This is picking up item 2, dropping item 2. So picking item 2, dropping item 2. So based, if I pick up item 2, this will stay as 115 because I still have 3 and 4 I can add. If I'm dropping 2, then you have to recalculate the value of fractional knapsack using, so I'm dropping 2, so just leave this out and then consider this, pick up this 2 10 makes it 12, and then 4 more from this, so 4 2s 8, so 8 plus 50 plus this, so this becomes 98 if I am picking keeping 1 in consideration, 3 and 4, so this will be still 98. So 0 and 1, again you have to calculate. You're dropping 1 and you still have 2 3 4, so this will be 82 again. And if you are dropping 1 and 2 both, then 60 is the maximum profit you will get. Okay, so is this clear, this part? Because this is important and rest is simple, just like your 0 1 knapsack using a tree. So you calculate maximum profit a node can give you. We take the based on what we pick and what we drop based in our tree, we calculate maximum profit using fractional knapsack, not using 0 1 knapsack. And we use this fractional knapsack maximum profit as a means to achieve a reduced state space tree. It helps us in bounding our nodes, which we'll see in a while. Okay, so So this is what the next 2 3 slides do. They calculate the profit based on fractional knapsack. So they are also getting 115 here as the maximum profit. Then, okay, this we'll discuss on the. So they're getting 82 if you're dropping and picking something. So this is actually the solution that you will get. Okay. What I want to do is I want to actually do it on the whiteboard. So 40, 30, 50, 10. Okay, so this is your problem. We'll do it for a few notes and then we'll move to the actual calculated one. So there are 3 things which we will calculate. One is the profit. Profit means whenever you pick an item, you see how much profit it is giving you. So if I pick up item 1, I'm getting a profit of 40. And if I pick up item 1, I get a profit of 40. I get a weight of 2. Basically, you can use weight 2 is used up, right? So your weight cannot exceed 16. So when it's under 16, it is a node that you can explore further. So it is a feasible node in terms of your static bound. Your static bound is that the weight that is in a particular node should not exceed 16. And we have this max profit that we just now calculated. So when you are at the starting point, actually this is not what you'll have here. So I'll put three values in every node. One is the profit, this, and the other is the weight, and the other is the max profit. Okay, in the same order. So when you have not picked up any item, your profit is zero, your weight is zero, and your max profit is 115. What is this max profit? It is the maximum profit you can have using fractional knapsack, considering your current state in the problem. So you have just started the problem, you are at node 0, you have not picked up any item, you have not decided to leave any item. So your you are you can consider all the items available to you, and you can have a maximum, at this point you can have a maximum profit of 115. Now comes the step where you decide to uh, pick or to drop item number 1. So if you pick up item number 1, your profit goes up to 40 because the value of item number 1 is 40. Your weight is 2 now. And what is your max profit? Since you have picked up 1, you still have item 2, 3, 4 available to you. If you calculate using fractional knapsack, you will again get a maximum profit of 150. And if you drop it, you are at 0, 0, and what is your maximum profit? If you strike this off using fractional knapsack, what you can get is 82. Okay, so this is how you are exploring this problem to find a solution. Now we need to apply both your static bound and your dynamic bound. What is your static bound? Weight should be less than or equal to 16. If you exceed the weight, if the weight is greater than or equal to 16, then it is not a feasible node, because it's not going to give you a solution for 0, 1 knapsack when you're exceeding, or for any knapsack. You cannot exceed the weight. And now what is your dynamic bound? Now dynamic bound will depend on uh, something which I will let you know. So let's do one more and then we'll go back to the picture. So because I don't think I'll be able to draw all of it then. So pick item 2, drop item 2, pick item 2, drop item 2. If you pick item 2, you get 77 and 77 and 115 continues to be there. And if you drop it, you get drop it, you are still at 42. And what did we calculate earlier? Calculated 98. So if you're picking up 1 and dropping 2, so you can get 90 and 98. 428, yes. And here again you can get you are dropping 1 and picking up item number 2, so profit of 30, weight of 5, and 82. And if you drop this, so 0, 0, if you look at it, you can at most have 60 because you just have 3 and 4 item left. So this max profit basically tells you what, if you explore this node, what is the maximum profit you can get out of it. So looking at max profit, you will decide whether to explore it or not. So for example, mm, I have something like this. So this is my current value. Uh, this can be some weight X. And this is my max profit. um, it's not likely, but this is a hypothetical situation. So if you see that what you already have is more than what this is promising you, that means it is not a promising node. In the sense, you already have 80. So this node tells you I can give you a maximum of 30. So why would you go and explore? And this 80 might not be here. I'll tell you what this where this 80 will come from. So so when we expand this tree further, we will have this tree. Okay, if you see they have not expanded the, wait, let me stop this share and go back here. So this is the same tree. If you look at it here, you don't see those two nodes here, and I'll tell you why those two nodes are not here. Okay, we actually drew that. We had it is 1 and 0. So when it's 1, 35 and was it? I think 60. So get 0, 0 and let's go back to the whiteboard. So 35 and 82 and 0, 0, 60. Okay, I lost this now. 35, 82, 0, 0 and 60. Okay. Now, if you see the red numbering on the tree nodes, this is the order in which you are traversing the tree. Okay. Based on this order, you will see that our dynamic bound will prune the tree in different ways. So when I start exploring my tree from here, okay, this is my starting point, and this is a promising node because what my current profit is, my current profit is uh, okay, they have used different terminologies here. So this is my current profit, that is, you can say they have used max profit for what you are having currently in the tree, actual max profit. So what this 115 is, this is the, you can say the estimated max profit this node can give you. So let's name what do we name them? Okay, okay, so you can say this max profit, and this is your I'll just name this 115 as estimated profit, and your current zero value is max profit up till now. Okay, so when you are at node 1, up till now, obviously you're not made any decision, your max profit uh, for the actual profit is 0, and your estimated profit is 115. So when you compare your max profit with the estimated profit, obviously your uh, I'll write it like this: if your estimated profit is greater than your max profit, then you explore the node, because estimate is telling you you'll get a better profit if you explore this node. Otherwise, if your estimated profit is less than your maximum profit, and what is the maximum profit? It is basically, uh, as you are exploring the node, it is your uh, what is the maximum profit you have achieved till now. So let's explore the tree. So one is a promising node. You expand it. Okay, you expand. You know you have two options. Either you will take or leave item number one. So this, what you are marking, this 1 2, this is the order of traversal of the tree. You can do a DFS, you can do a BFS, or you can do a, we call it best first search. So we will traverse the node based on whatever seems best at the moment. So we'll do that later. So this one is a depth first search, so let's go with that. This is a depth first search. So you are traveling like this: 1 2 1, 2, 3, 4. Then you're actually coming back to this 5, 6, then coming back to 7. You're going 8, 9, 10, just like we do a depth first search. So if we had to go here, this is how we would do the right branch. Okay, so this is a depth first search. Once I expand the node, the next node I will visit is this one. So the values are already filled in. So what I do is my max profit changes to 40 because now I have a profit of 40. My weight restriction, I'm still within the weight limits. Because I am picking up one, I still have an estimate of 115. So let's go here to the next node. When I pick up, this is all one picking up. When I pick up item number 3, I get a value of 70 total. So I change my max profit to 70 and weight changes to 7 and 15. Then when I pick up the fourth item, my value goes to 120. Okay. Obviously, because the weight is going to 17, which is exceeding the limit. So because I am exceeding the limit, it is my, here, this is my static bound. I cannot, this is not a solution, and I cannot update my max profit because of this, because I am hitting an infeasibility condition. This is not feasible. This is not a feasible node. So I will not update my max profit, and I will not obviously explore it any further. If at all there was some other node I had to explore. So I will backtrack, go back here. I have another option available. I will go to node number 5. So node number 5 means I will drop item number 4. So what I get out of item number 3. So what I get is a profit of 70 and 7 weight and estimated profit of 80. This estimated profit is changing because you are dropping item number 3 here. So you have to recalculate using fractional knapsack for item 1, 2 and 4. Okay. So you are getting this. So what is your max profit at this stage? When you were at node number 3, max profit was 70. Here again, max profit is the same because you are not picking up any node. Now you have two more options from here. This is giving you 80. So you will update your maximum profit to 80. And this one is giving you 70. So you will update your maximum profit only if the profit you're getting is more than your current value. So 70 is less. So currently they have marked it N. Why? Because we are yet to explore the other side, and we have no other place to go from this. Okay. So using a depth first search, this is the next node we are getting to. In this node, you get the profit is 40. So obviously, this is the profit you get by following this chain. And obviously, what you have already explored using DFS in one branch, you are getting a profit of 80. So obviously, you will not update your max profit. Your max profit is more than 40. So this gives you two more options with a profit of 90 in node number 9, and this one is still 40. So now max profit updates to 90. Okay, so you go to 8, then you go to node number 9. Now you go to node number 10. Again, it is not a feasible node. So you come back here and no update because you're not adding any more item. So this is one node. Currently, the value of this node and the max profit is the same. So you come back and you come here. Now, what is your, in all the nodes that we have explored till now, if you see the max profit is less than the estimated profit. So let me just mark it here. So I was getting 98 here. Here my max profit was 70 and what I was expecting is 115. Here it was 80. So that means I have reached the best I can get out of this branch. Uh, I had 80 before coming to 7 and this gives me 70. So it's not a good node for me to explore. When I came here, I get a max at node number 9, I get a max profit of 90, and it is still telling me that you can get 98. Here it's still telling me that you can get 98, so I decide to explore it in further. On exploring further, I find out that this left node here is not feasible, and right node, now my max profit and my estimated is the same, so obviously this branch is not going to give me any better, and there is nothing more left to explore. So I go back and I come to my next node in order of traversal. Now I'm at node number 12. Node number 12, the profit here is 40, and it says that I can give you at the most, the maximum profit by this branch is 50. But what I have already, I have 90. So what I have, my maximum profit is already more than your estimated profit for this node. So I do not need to explore this node. And this node is pruned because of a dynamic bound now. Why is it is a dynamic bound? Because based on your order of traversal, if you did it by breadth first search, maybe at when you reach this node, your max profit is not 90. It all depends. So max profit is a variable that gets updated as you traverse the tree. What is inside these nodes, these three values, they are going to be the same. So first you draw this tree completely with all these, because we are doing it on paper, we need to draw. When the system does it, it'll explore a node only when it thinks it is feasible. So for you, you need to draw this whole tree. Then based on your order of traversal, you will keep updating your max profit, and max profit will help you decide whether you should prune this branch or not. Here max profit is, if you see, 50. What this node is promising me is less than what I already have, so I will not explore this. So this is my dynamic bound. This is not a static bound, because it was well possible that when I reach this node, exploring this node in some order, I might still have a max profit of 40. So then this was a promising node for me. But now, based on how I have explored the nodes in the tree, my current value is 90. So I know exploring this is not going to help me. So this is a dynamic bound. Your static bound is this one. 17 is greater than 16 and 17 is, this is your dynamic bound. So when you come to 13, again same happens. I have 90 with me, it's promising me 82. That's why they have not even drawn this side of the tree, because they have just pruned the tree right there. Okay, so how do you solve 0 1 knapsack using branch and bound? Is by constructing this tree with three values: the profit, the weight, just like you would do in a simple uh, fixed tuple state space tree, and you have a third parameter which is known as the because it's an optimization problem, we are putting what this node can possibly lead us to, that value, or you can say the estimated profit for by exploring this node you can get is 115. But you have some limitations with respect to weight, so you have to prune your trees accordingly, and you also will explore a node only if it promises you better than what you already have when you are searching the tree. I'll show you one more example. Just clear this. Okay, so this is another 0 1 knapsack problem with branch and brown pruning. Okay, so what you have here, you have these are your, just a second, straight the your item one. This is the list, your item and the weights. Okay, it's a 0 1 knapsack problem. So they are again putting current profit, current weight, and upper bound on possible profit from adding further items. So if you look at these four items here, if you arrange them, item one is value 10 and weight 1. Item 2 is value 18, weight 2. Item 3 is value 32 and weight 4. And item 4 is 14 and 2. So they are already in the decreasing order of their value per unit weight. It is 10, 9, 8, and 7. So if you try, what is the upper limit of your weight is 6. W is 6. So you can pick up 1, 2, 3, and 3. 52 is the maximum you can pick up if you have all the items available, which you see here. So again, you have to make this tree using the 0, 1, include or exclude item, and then you draw the tree. Now, this again is a depth first traversal. So you see the nodes are numbered 1, 2, 3, 4, 5, 6, 7, so on in the depth first search order. So, just a second. So this internal node value calculation is easy. You just have to remember when you are including or excluding, you have to recalculate the estimated profit. So at the most you can get is 52. Okay. So let's do the traversal now. I start at 1 and I go to node number 2. There my profit becomes 10, weight is 1, and estimated profit is still 52. So my maximum profit is 10 currently, what I have actually in my SAC. Then I come to node number 3, my profit changes to 28. I come to node number 4, my weight, this is a static bound. Because of the weight, I cannot go any further. So I come to node number 5. My max profit is still 28. When I come to node number 6, my profit is 42 and my estimated profit is also 42. So I cannot get any better. So my current profit is 42. Here, when I come to this node tells me that estimated profit is 28, but what I have already is 42. So this will be a dynamic bound. In a way, it is you are exhausting your items at this stage also, but technically it is a dynamic bound because this node is not promising you better than what you already have. Then coming to node number 8, your what you have when you have explored this tree up till this point, your maximum profit is 42. So when we see here, it says I can give you 49. So I will explore this node. So this gives me two options. One option is still promising me 49 and another option is promising me 24. So 24 is less than my current value, which basically I'm traversing the tree and I already know some node is giving me 42. So I don't need to explore a node that is promising me 24. So coming to here, actually when you come to 10, this is a static bound because of weight, and this is also a dynamic bound because it's not giving me better than 42. Again, this is a dynamic bound. When you come here, your profit is 0. Your current profit is 42 and it is promising you 50. So I will explore this. When I reach here, it is again promising me 50. So I'll explore it. So I'm actually getting 50 at this node. So when I'm getting 50 at this node, my maximum profit also updates to 50. So when I come to the next node visit, it's promising me 32. So this becomes a dynamic bound. And then when I come here, it is promising me 46. So again, this is a dynamic bound. When they've written less, if it is less than maximum profit, so it's a dynamic bound. So you see, look at this tree, and I'll just go to the next page. The next page is the same problem, but with a breadth first traversal. So look at the tree. Because of the breadth first nature of the tree, you see there are more nodes here. So same problem, but because so same problem here, this is what we did, and this is again, if you see the order of traversal is like this: 1 2 3, then 4 5 6 7, then like this. So obviously when you're traveling in a different direction, your maximum profit values are going to be different, the current maximum profit, and based on that you might be exploring more nodes than you would do otherwise, or less nodes, it depends on the conditions. So here again, you start here, you go here, maximum profit is 10, expected is 52, so you will explore it. So you will expand this, put it in the queue, then you'll come here. This is also promising, you'll expand and put its child nodes in the queue, then you will come in order. The maximum profit is 28, 52, still a promising node. This is again a promising, this is promising, this is promising. When you reach here, this is a static bound because of weight. This is still promising because your maximum profit is still 28. So this is promising, this is promising, this is not promising because when you reach here, you have updated your maximum profit to 42. So this becomes a dynamic bound here. Then this is again promising because you're not getting anything more than 50. You stop here. This 32 is less than 50. So this is a dynamic bound. This is a dynamic bound. This is a dynamic bound. Here again, dynamic bound. You'll see the dynamic bounds. This is static bound. This is dynamic bound. So this is the tree will slightly be different, and the bounds based on which the node is pruned will also be different. Now, going to the next one. So let me just clear it off. This is again the same problem, the same tree. If you look at this tree, it is quite sparse compared to the previous counterpart. So now, what is the difference here? The way in which the traversal has been done in this case is, this is the best first traversal. So what does it mean? When you explored your current first node, when you actually take the first step, you explore and you have two nodes, one in which you picked up item 1 and one in which you excluded. Okay, this gave you 10. Okay, which is the maximum profit so far. So this is the best node for you out of these two. You had two and let me name them, A and B. Okay, out of A and B, A was seems better because it's giving you some profit. So I will explore A first. So if you see the numbering, this is 1, this is 2, and I when I explore it, I get 28 here. So this is obviously a better node than you can say. Now B is also in the queue, C and D. Out of C, D and B, C is the best, so I explore C. So I get 2. Well, this is a static bound, and let me name this E. So I've explored C. This is after 28. Okay. What is your node number 4? Sorry, we expand based on the maximum profit it gives us. So this one is giving us 52 and this one is giving us 50. So we took 52 one. Again, this one is giving us 52. So we took C first. And then when you check, this one is giving you 42, 49 and 50. So number 4 node is this. You expand, you get 50 and 46. This will be 5 because it is promising you 50. So then when you expand this, you actually get 50 here, and this one is giving you less than 50. So this becomes a dynamic bound and dynamic bound. So if you look at it, this is again number 8. This is number 6 because based on the order, you are not getting as much profit as your current profit. So you will prune them right there. So you will expand a node based on best first of your expected value. So if somebody is telling you I'm giving you 52, so I'll explore 52 one first and leave it for later. So all my like I told you in the last class, you have a live node and you have a e node. So e node is something uh, you have explored and you have put it in the queue, so it is still there. The node you are currently at is your live node. So which one will you pick up next will depend on, in case of depth first search you are following the stack order, in case of breadth first search you are following the queue. This is also a queue, but this is a priority queue, so the next node that you take up to explore will be based on best first. So whichever node is offering you a better value, you will pick it up first and then work on it. So if you see 52, this is number 1, 52 number 2. So at that point you only had these three, so 52 is better. Then this gives you again 52 number 3. So and you have 49 also, but you're not going there because after 52 you have 50 as the better choice. Then 5, obviously 50 again. 5 is a better choice. After 50, the next choice is 49. So you pick it up to explore, but you see that it is a dynamic bound, so you do not expand it any further. Then 46 is the next better value, so 7. Again, it's a dynamic bound because of your current, in the order in which you have visited, your maximum profit has been updated to 50, and so on. So your tree size space will also depend on your ways of traversal. So the basic traversal mechanisms that we use are these three. Best first. You can define your best in different ways, so that can again alter the order in which the nodes have been visited. So we are doing 0-1 knapsack using state space tree by just deciding whether you pick or leave an item. You can do it, let's say, without this estimated value, and then you'll get all the solutions, and you can check all the leaf nodes with the maximum value, except for the ones that are pruned for the static bound. Okay, if you don't have a dynamic bound applicable, if we don't ask you to do this in this manner, you just do a 0-1, you get all the possibilities, and then you select whichever is giving you the maximum within your static bound. But this is an optimization problem. We want to explore something only when it is a promising node. What does it do actually? Dynamic bound helps us to reduce the state space tree. Static bound also does the same, but dynamic bound is an additional factor or criteria that will, because this tree is not actually there, you are actually exploring the problem for all the solutions, and you do not go and take all the paths in the tree, because all of them are not going to go to the solution. So we restrict, basically we're trying to make it efficient by restricting or by not visiting or exploring nodes that are not giving us anything good, that are not promising to us. That's the terminology they use. Okay, so any questions? So when is your first paper? Monday?
Ninth. Yes, mom.
9th. So do you have break between papers? No.
No, mom.
Okay, so today's Wednesday. So if you want to take a break for your midterm, we'll take this classes after midterm then.
Yes, mom.
Fine?
Yes,
Or you
mom.
want to take classes?
Mom, we want to take the break.
Oh, you want to take it? Okay, fine. So today will be the last
We
class
have to prepare for the
midterm. Okay, if you have any questions, you can just email me. Uh, This one, we still have to do little one couple more examples of backtracking problems. So we'll continue after midterm. You can
मैम
take yeah.
मैम कैन वी गेट मोर टेस्ट और मतलब क्या हमें ऐसा कुछ मिल सकता है जिससे हमें पता चले कि एग्जाम किस किस हिसाब से होगा?
हम्म, अगर मैं मॉक टेस्ट भी बनाऊंगी फिर कहाँ से इतने सारे क्वेश्चंस लाऊंगी. व्हाट यू कैन डू इज आई विल गिव यू सम सैम्पल क्वेश्चंस एक दो टॉपिक्स में से so that you get me. So I'll there'll be
मैम
what I am planning to do is I have not made the paper yet. So there'll be some objectives which will be straightforward, like 1 marks, like a simple multiple choice question. And there'll be some with 2 marks where you will have to do some kind of, let's say, calculation. Okay. So maybe not that those will not have options, they'll just have a text box to fill your answer. Okay. So that because options होंगे तो cheating करनी और easy होगी ना, A B C D. तो ऐसे at least calculate करोगे, there might be some uh, what you say, you all of you might not agree to the same answer. So अगर options नहीं है, so all of you will write. So maybe a few fill in the blank types also, and maybe a multiple choice mix of all, whatever I think. So होगा कुछ नहीं,
But ma'am,
if you've done the
30 minutes.
टी शीट्स जो किए हैं उसी टाइप के क्वेश्चंस you can expect. If I get time to make something mock, I will send it to you. Okay. Aman, did you take the attendance?
Yes, ma'am.
Okay. All right. Good luck for your exams. Prepare well.
Thank you.
Okay. Thank you.